part today is the interpretation of an article that's already been published. You've read the article, you read these p-values, and you make a conclusion based on that. Because the thing is, the article's not going to tell you what the p-value means. It's going to put an assertion forward. It's going to give you the p-value as support of that. And then your job is to understand what that all means. And I discovered about 5 years ago that I was glossing over that and going straight to the let's run the math. And students were trying to learn two things at once then. How to run the math and how to interpret the result. And I discovered, I'm like, that's a little too much. Let's split it out, which is why we've been sitting in this for a week now of the PowerPoint slides. If anybody needs the slides, I've got them here, and the article list if you need a reference. So I've got those here if you need them. Make sure if you grab the slides, there's 3 of them, 3 printouts of them, so make sure you grab those. And I want to get into those, a recap again, and then make sure via the in-class quiz that we can read an article correctly and its conclusions correctly. And more importantly, I personally think more importantly, we can also understand the limitations of the results. The limitations of the result. Because I think that's, in my opinion, that's really what statistics is all about, is being able to measure that uncertainty. Or at least recognize there is uncertainty, and even if we can't get a number, we can get a relative size. I should be more worried about that than that. And then, once we've got a kind of a lock on that, we're going to start testing flu vaccines, and infant medication, and Florida motorcycle death rates, and all kinds of stuff, other stuff. We're going to take it all out, talk to all these different contexts. I've been trying to collect data that applies to as many different fields of interest as I possibly can to show you how far-reaching this stuff can be. Hopefully I've succeeded. I keep finding more. So, interesting, actually speaking of that, you know what, not right now. Remind me to tell you about the temporal study that I just heard about 15 minutes ago, walking down to class with a colleague. Temporal study, remember. And you can just say 90s, I'll probably remember it. Say 1990s and I'll remember that. Cool? Somebody do that in the next hour and a half. Okay. This is the last couple slides from the handout. So we've talked about what the conclusions are for a hypothesis test. You can be wrong. There are 4 things, there are 4 conclusions and results that can happen when you run a hypothesis test. Let's go through them 2 by 2. So you get a small p-value. Remind me what that means. You get a small p-value. What is a p-value? Why does a small p-value attract your attention?
In the 5% area of the bell curve.
Good. And what's the Brandon, thank you. We're now in the 5% area of the bell curve. We're outside of the 95% area of the bell curve. Why does that get our attention? Oh, it's an outlier, which means it shouldn't be there. Maybe it belongs in its own curve. I like what I'm hearing here, Good, good. So that the presence of that being so far away from where it should have been grabs our attention. It grabs our attention and it says, hey, maybe something interesting happened here. Maybe. Now, maybe nothing interesting happened. Maybe it was purely just an outlier, and if we run the test again, we're going to get data that's closer to where we think it should have been under the null, right? So what's the way we can be wrong? We say something has changed. Well, we could be wrong, right? We could be wrong, right? We could be wrong. Yes? Yes. What's the chance? If we are at 95% confidence, the chance we're wrong, as it always has been, is 1 in 20. Very nice, 5%. I like how you guys go back and forth between 5% and 1 in 20. Thank you for that. I'm learning more and more as I do this job longer and longer. People have a real problem with fractions and percentages, and I just so stoked you guys are just like, 1 in 20, 5%. Yeah. 5 out of 100. It's good. Keep that going. That makes me happy. Gives me hope for America. All right. So some formalities. We usually call that alpha. It's often called the level of significance of the test. That's more of that snooty language, these are often called tests of statistical significance because you're trying to show a significant deviation from what you were expecting. So the formality of it is little alpha, this is a lowercase a in Greek, is usually set at 5% because we usually set our confidence at 95%. As we go through the next 5 weeks, we'll see why we don't always want that. I did put a link up for you guys a couple days ago in the extra resources area of your schedule page that discusses type 1 and type 2 errors. And while type 1, which is what this false positive is called, is generally set at 5%, you can see reasons why you don't want that sometimes. It all depends on context, which we're going to be talking about dozens of times over the next 5 weeks. All right. So here was the conclusion from the secondhand smoke article. most lung function parameters were significantly reduced. Okay, so that implies something changed. Because when we went into the study and we stuck those people in the box filled with smoke, what's the null hypothesis? That nothing was going to happen to their lung function. It seems naive to think that, right? You take a person, you stick them in a box full of smoke, and you're going to assume nothing's going to happen with their lung function. It seems naive, doesn't it? But why does it seem naive? Why does that seem naive to assume that nothing's going to happen to their lung function? Because it's 2014. It's 2014, and we know that smoking's bad for you. But if you asked that question 100 years ago, that wouldn't seem naive at all. Because smoking was fashionable. And nobody even thought about the health implications of it. This is cool. You're worried that you're coughing? No, I'm not worried at all. But 100 years later, we now know that it's bad for you, so it seems naive. But whether it seems naive or not, that's how you set up a statistical test. You draw the curve, you slap the average in the middle, baseline, and you say, let's see where we are at the end of the test. Oops, we're down here. Something changed. There's the indicator that something changed. So our conclusion, oh, Tom, go ahead, Ted. No, oh, you're good, you're just with me. Okay, you're tracking, this is awesome, makes me happy. So we just said that most lung function parameters were significantly reduced. What if we're wrong? What if we're wrong? That means we said that most lung function parameters were significantly reduced when they weren't. That's all you have to know. You said something changed when it might not have. That is what a type 1 error is. A false positive. You're falsely positive. You're false because you were wrong. That's the false part. The positive part is because you said something changed when it might not have. Does that make sense? That means if you run this study 20 times, you are going to get a false positive result 1 out of every 20 of those times. This is why it's so crucial, friends, to do what to studies? To replicate them under identical circumstances. Because if you keep replicating the results under the same circumstances and you keep getting the surprising results, you stop thinking it's surprising. You start saying, oh, it's replicable. That means maybe what we're studying is actually holding up. It's actually holding up. We just celebrated Dr. Jonas Salk and the polio vaccine like 2 days ago. Surprising result, polio, this terrible, 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 terrible sickness. Here comes Dr. Jonas Salk with one study that shows he has a vaccine for it. Do we believe Dr. Jonas Salk after one study? No! We send it out, we farm it out to dozens, if not hundreds of labs and do it again. And after it's been replicated beyond a reasonable doubt, we say, we think we have a vaccine. Does that make sense? You guys getting that fact? Hopefully you're getting that fact. Good, good. So you can be wrong. It's possible you get a false positive. The way to metric that false positive, that reminds me. The way to metric that false positive is replicate the study again and see if you get the same positive test result. It's harder to believe 2 false positives. How many of you guys have been told or heard if you blow a DUI and you know you're sober and you blow a DUI to take the test again, to demand a second test right then? Or you take a disease test again if you think you're clean, you take a disease test twice. Because if the first one was a false positive, that means you should have a very good chance of a negative test result the next time. And then you've created reasonable doubt. You have not created beyond a reasonable doubt. If you test twice positively, that's kind of beyond a reasonable doubt. Then it's like, dude, come with me. But if you create reasonable doubt, that's the whole point of the justice system, at least in theory. Does that make sense? Fair enough? Good, good. Okay, I'm gonna write one thing down. Truth, where's the, I got an idea for a quiz for next week. Okay, cool? Okay, good, good, good. Okay, now here's the other way. So there's 2 ways. We just discussed 2 possible interpretations of a hypothesis test. You get a small p-value. Now if you get a small p-value, the training statistically is something changed. Positive test result. And we just got done talking about a false positive, right? False positive. Is there such thing as a true positive? Of course there is. Of course there's a true positive, right? Of course there's a true positive. A true positive, contrary to popular belief, is actually not 95% likely. We'll get into that more as we go through this class. It can be, but it isn't guaranteed to be. The idea of a true positive is Something changed and you caught the change. So in other words, secondhand smoke actually does damage your lungs, and you correctly identified the fact that it damages your lungs. Now that is not necessarily a 95% likelihood of a true positive. It seems like it should be, right? Because if a false positive is 5%, it seems like a true positive should be 95%. But believe it or not, if a false positive is 5%, a true negative is 95%. If that makes your head swim right now at 8:40 in the morning, it should. And don't worry about it right now. I have a whole project I'm designing to talk about that idea, if that's okay with you guys. So don't worry about that right now. Just realize that false positive is 5% likely. True positive, hopefully, it's called the power of a test. Hopefully, the true positive power is high enough based on your sample size to catch that change if the change happens. That's all a true positive means. True positive means, hey, I think your lungs are worse than they were an hour ago. And you were right. That's all a true positive is. Your lungs are worse, and you're right. I mean, it sounds terrible. It's all we're about damaging lungs, but the idea statistically is you made the right conclusion. Fair enough? If you're couching it in terms of the cards we did from class 5 weeks ago, you guys said, hey, that deck is rigged. A true positive would be the deck actually is rigged, and you correctly said it was rigged. Make sense? A false positive would be, you said the deck is rigged, but the deck is actually totally fine. Totally good enough for government work, so to speak, on it, yes? Good. But those both come with a small p-value. Those both come with a small p-value. How about a large p-value? What does a large p-value mean? What does that mean?
That it fell where you expected it?
That it fell where you expected it to fall, Aaron. Thank you. You drew this null curve. You drew this null curve. And you said after 3 hours, lung function is going to be back where it started. And guess what? It is. You landed back in there, right? You landed back in that curve where you expected it to be. Large p-value. So you put your hands up and you go, well, nothing to see here. Nothing to see here, folks. That's essentially what statistically this is saying. That's a negative test result, isn't it? Nothing changed. Negative test result. A positive test result means something changed. Something surprising, or something appears to be surprising. Negative test result, nothing surprising at all. Nothing surprising. Good so far? And if you're right, good. That means nothing changed, and you said nothing changed. Notice how we didn't have a negative test result on the first day of class with the deck of cards. Because you guys weren't okay with the deck, were you? You guys were pissed at the deck. If you're okay with the deck, you'd have been like, yeah, whatever, 5 black cards, I'm out of here. That would have been a negative test result. The statement that everything's cool, everything's usual, everything's as I expected it to be. That's what a large p-value shows you. The likelihood is high to get the result, therefore nothing surprising happened. Now, even if you get a large p-value, could you be wrong? Yeah, you could say, you know what, your lungs are totally fine. Your lungs are totally fine after 3 hours, but that might be in error. It might be that they're not and you missed those, yes? Now, what kind of error is that? It's a false negative conversationally. Statisticians, for whatever reason, call it a type 2 error. I just read a very convincing article yesterday. If you had me in 243, we had this discussion about skewed left versus skewed right, and how I was taught by statisticians how to recognize it. You recognize skewed right by looking at the distribution, and you look at where the hump of the curve is. And wherever the hump is, you say the opposite. And I thought to myself, that's the dumbest possible way to teach somebody something I can think of. Think of what you think is right and then say the opposite. This is why students hate math classes, because of crap like that. So I just ruled out, I said, just call it skewed. We'll determine where the average is as we go through the class. Type 1 and type 2 errors, I just read a similar article last night written by a statistician. Conversationally, they are accurately called false negatives and false positives. But more traditionally, we call them type 1 and type 2. If it's conversational, accurate, and effective, why not just call them false positive and false negative? You see what I'm getting at? I love the fact they're called false negative, because you get 2 words right there. Why is it false? Because you were wrong by saying it was a negative test result. And why is it a negative test result? Because nothing changed. There was a negative change. Negative significant difference. I love that term. So why type 1 and type 2? I have no good answer for you guys. Because it is. Because it is. Because we failed to reject the null? Whatever. Just realize it's out there. I like it when you guys call them false negatives and false positives. Now it could be a true negative. Yes? It could be a true negative. A true negative, that's confidence. That's your 95%, your true negative. That's the actual other side of the false positive. It might not make any sense right now why true negative and false positive should be equal parts of the same curve. It might not make any sense right now, and that's okay. I don't expect it to right now. So I have a project devoted to it. It used to be just 5 minutes of a lecture, then it became a quiz, and I began to realize, I'm like, no, it should be its own project. So I'm building that right now. So, true negative, false positive, false negative, true positive. And we'll get to all that stuff as we go through. Fair enough? The type 2 error is usually called B for little beta. What is the probability of beta? This is a trick question. This is a trick question. What is the probability of beta?
35%.
This is a trick question. What is the definition of a trick question? Question that? Well, it tricks you, but it has either no answer or not one correct answer. It's a trick question because in order to know what beta is, you have to know where that other curve is that I keep drawing. I draw the null curve, right? And I slap an average on the null curve. And because I know where that average is on the null curve, I can move over to standard deviation and draw a brand that's 5%. Is that believable? We know it's about 1.645 standard deviations over. Will give us 5% at 95. We know that because we know where the center of this curve is. Remember the other curve I started drawing in yesterday? That other bell curve? Sometimes it's close, sometimes it's far. Where is that curve exactly? We don't know. We have a hunch as to where it is. When we get extraordinary outliers on the null curve, we assume the other curve is around that outlier. But that's not an exact location. It's an implication, which means we don't know where that one is, which means we can't measure 1.645 off of it, which means I can't give a concrete value for this. Again, this is why there's a project attached to this whole idea, which we'll get to. Last project, right about the time you're completely sick and tired of dealing with it. All right, so here is a negative test result from the last study, the secondhand smoke study. We stuck them in a room for an hour, measured their lung function. It's terrible after an hour. P less than 5%. Then we took them out. We took them out, stuck them in a clean room. Let the lungs do their thing, let the alveoli do their scrubbing. What it looks like, right? Like that. 3 hours later, blow into this tube. Look at that. On average, even with plus or minus, your lung function looks exactly the same as it did before we started. Therefore, not reduced. Negative test result. Yeah? Negative test result. Not reduced. Negative test result. How do we indicate significantly not reduced? P-value's too big. What's too big? Bigger than 5% for now. For now. We'll mess with that, I promise. Bigger than 5%. Could we be wrong? Hell yeah, we could be wrong. Because we could say that their lung functions are just fine, but it could be a false negative and they might not be fine. This is, in my opinion, personally speaking, this is a worse error for this particular case. It is my opinion now. A false negative for something with health reasons is generally, in my opinion, is generally worse than a false positive. Because a false negative can let an underlying condition lay residual in the population unchecked and untreated. Whereas a false positive brings healthy people in for more screening. And now that's an inconvenience, of course, right? That's an inconvenience. But generally there isn't going to be a negative health effect on that. If you ignore people that have a medical condition that could be treated in the population because your testing missed it, that I think is a bigger deal. My opinion only. My opinion only. But, is that fair? You guys get that? Okay, good. I'm going to keep asking you that question too. In your opinion, which is worse? Listen, please.
That statement is a true negative.
If we're correct, if indeed, and here's the if, right? If indeed lung function is unhampered, this is a true negative. Because lung function is unhampered, and we said lung function is unhampered. Now the problem is, only one of those two things is known for certainty. The fact that we said it's okay. Are we ever going to know beyond a shadow of a doubt if the lungs are actually okay? That's the trick. That's why this is called probability and statistics and not check please, go home, we're done. We have to be able to measure these errors. That's what we're getting our feet under us now, to measure that. Because the first thing somebody's going to say is, what's the power of your test? And what's great is, as I was listening to this discussion of the study I just heard about 25 minutes ago, as I was getting the nuts and bolts, it was on a very, very, very small sample. which means that very, very, very small sample has very, very, very low what is called power. That means it has a high, high probability of a type 2 error. Now, getting ahead of ourselves a little bit here. But that's what you have to start controlling for. Whenever somebody tells you, oh, the sample size is too small, you ask them, how big do you want it to be to avoid a type 2 error? Guarantee that'll shut them up right then. Because they haven't thought about that. All they're trained to think about is that sample is too small. You have to be able to answer that, how big should the sample be to make you happy? And when I say make you happy, identify a change. Because a negative test result will come if the change is there, right? And we miss it, that's a false negative. That could be bad. That could be very, very, very bad, especially with things like health and safety equipment and whatnot. Yeah, this hard hat's fine, we tested it. Really? Yeah, me and Jim Bob, yeah, it's fine. You put it on your head, go out and it's, but that cliff is eroding on top of me. It's fine, we tested it twice. You're setting yourself up for a false negative result right there. You're setting yourself up. It could be just fine, absolutely, but with 2 tests, you have to, anyway, you're getting the point. Elizabeth, does that make sense? Hope I didn't make it worse by that little 5-minute diversion, but that was good, very good question. Cool? Okay, good. Now, I'm gonna have a whole project about, this is the last slide in the sheet. This is the last slide in the sheet. I'm going to have all, this is where the project grew out of. So we're going to leave this for now and go, as we go through the course, revisit this constantly. Getting a small b-value and reacting appropriately, that is always a positive test result. Something changed. Just realize you might be wrong with a false positive. And the probability we're going to set it at alpha. Usually 5%. Usually. Large p-value and reacting appropriately, nothing changed. Negative test result. Negative test result. You could make a type 2 error. That one's the tricky one. That one's the one we have to analyze carefully because it's more difficult to micromanage that number. Don't worry about the quantity of it right now. We'll deal with that as we go through the course. What I want you to worry about right now is this. Grab one of these. Grab one of these. I'm going to keep one so I can refer to it too. Grab one of these. How many of you have ever heard